Hello, and welcome to this FMSP online revision session. This session is looking at the MEI Statistics 1 specification and the topic of the binomial distribution. We'll start by looking at the specification. The first 3 points really cover the ideas of spotting what the question is about, setting up the model, and doing some calculations. Parts 4 and 5 are not just about the binomial distribution, and you might be asked questions on that involve finding probabilities in other situations where you've got to work out how many options there are. The mean of your binomial distribution, otherwise known as the expected value of x, you need to learn that. And you need to be able to calculate expected frequencies of various possible outcomes from a series of binomial trials. So looking at some key points, our factorial notation, there are n factorial ways of arranging n different objects in a line. Do bear in mind that sometimes when counting the number of ways of doing something, it's easier to work out something bigger and subtract, particularly if you've already answered part of that in a previous part of the question. Do think of the question as a whole rather than in separate parts. Never restart a counting exercise without checking that you couldn't do it a quicker way by using some of what you've already done. You use the binomial distribution to model situations where you've got a fixed number of trials. There are 2 outcomes for each trial, success and failure, and those outcomes have fixed probabilities, usually designated P and Q, where P add Q is equal to 1. And of course, the trials are independent. Here is your probability calculation, your binomial coefficient n choose r, and then probability of success to the power however many successes, and the probability of failure to what's left. Importantly, remember that at least 1 is the same as not none, and it's usually much quicker to work out 1 minus the probability that x equals 0 than to work out the probability of 1, 2, 3, 4, 5 and so on. And do remember to make use of the tables if there are lots of calculations. You are expected to do that. You're not expected to do all the calculations by hand. And then finally, the 2 results that you need to memorise: the expected value of x is np, and the variance of x is npq. So let's have a look at some questions. It's a good idea to read through the whole question first. So here we've got 13 men and 10 women in a running club. We've got a committee of 3 men and 3 women to be selected. We're asked to consider how many different ways just the 3 men can be selected, and then the whole committee. And then we're taking any old random sample of 6 people and asked to find the probability of 3 men and 3 women. Do notice that although this last question looks rather hard, there are only 2 marks available for it, so we're probably going to be able to use some of the earlier work. So part 1, straightforward. How many different ways can you choose 3 men out of 13? That's just 13. Choose 3 on your calculator, 286. For the whole committee, we need to think about the number of ways of selecting the 3 women. And there were 10 women, so that's 10 choose 3. So the total is 13 choose 3 times 10 choose 3, which is 286 times 120, which is 34,320. Now for part 3. Well, our random sample of 6 people, there are 23 choose 6 ways of doing that. That's 100,947. That's all possible groups of 6 people, not just the ones with 3 men and 3 women. So out of that, the probability that the sample is 3 men and 3 women must be, out of the total number of samples, 100,947, the number of ways of choosing 3 men and 3 women, which we worked out on the previous slide, 34,320. That simplifies to 1,040 over 3,059, which isn't particularly nice, so a decimal answer is more appropriate. That's given to 3 significant figures. Okay, let's have a look and see how the mark scheme works for this question. For part 1, there is a method mark for recognising that you need 13 choose 3 and an accuracy mark for finding that correctly. For part 2, there is a method mark for realising that you need to multiply your previous answer by 10 choose 3 and an accuracy mark for doing that correctly, and you are allowed to follow through from part 1. And for the final part, there is a method mark for realising that you need 23 choose 6 on the denominator and an accuracy mark for your final answer, and again that follows through from part 1. Okay, a typical binomial question. We've got a percentage, 25% of the plants of a particular species have red flowers. We've got a random sample of 6 plants, so this is looking very binomial. Find the probability that there are no plants with red flowers, and then we take 50 random samples of 6 plants, so that's random samples of our random samples, and find the expected number in which there are no plants with red flowers. Okay, so for part 1, we've got a random variable x, it's binomial, 6 in the sample, probability that they are red is 0.25, and we want the probability that there are no red flowers, probability that x is 0, 0.75 to the power 6, which is 0.1780. And you might easily have found that without actually thinking about it being binomial, because probability x is 0 is something you could have done before you knew about the binomial distribution. For part 2, we've got a new binomial distribution, and therefore should give it a different letter if we used one in part 1. And this time we've got 50 samples, and the probability that they have no red flowers is what we've just worked out, 0.1780. The expected value of y is therefore NP, which is 50 times 0.1780. which is 8.9. Okay, mark scheme for that question. A method mark for 0.75 to the power 6 and an accuracy mark for 0.1780. And for part 2, a method mark for doing NP and an accuracy mark for getting 8.9. Okay, let's look at a slightly more complex question. This is part of a question because the remainder of this question looks at hypothesis tests, which is in a separate revision video. Mark is playing solitaire. The probability that he wins is 0.2, independently of the other games. Find the expected number of wins in 12 games, and then the probability of exactly 2 and at least 2. So again, this is a binomial question. So I'm going to start by saying that x is binomial, 12 games, probability of winning 0.2. The expected value of x is then NP, which is 12 times 0.2, which is 2.4. And for part 2, A, the probability that x is equal to 2 is 12 choose 2 times probability of success to the power 2, 2 wins, and the probability of failure 0.8, there must be 10 losses. That comes out to be 0.2835. And for part B, probability that you win at least 2, so that's probability that x is greater than or equal to 2, is the 1 minus the probability that x is less than or equal to 1. Stop and check that we've got that right. I want greater than or equal to 2, so I want 2 in my answer, I don't want 1, so I'm going up to 1 and not including 2 in what I'm taking off. So that's 1 minus, and then I read off the tables. N is 12, P is 0.2, probability that x is less than or equal to 1, 0.2749, and that comes out to be 0.7251. Looking at the mark scheme for this question, there's a method mark for multiplying n and p, and an accuracy mark. Notice you're not supposed to round that answer, and if you do subsequent rounding you won't get the accuracy mark. For part 2, there's a method mark for 0.2 to the 2 times 0.8 to the 10. There's a method mark for multiplying 12 choose 2 by 0.2 to the something and 0.8 to the something, and an accuracy mark, correct answer only, for 0.2835. For part B, there's a method mark for noticing that the probability you want is x less than or equal to 1. There's another method mark for subtracting that from 1, and an accuracy mark for getting 0.7251. Well, that's the basics of the binomial distribution. This topic is continued in the next video on hypothesis testing. Do join me for that one, and I'd like to wish you all the best in your exams. Goodbye.